So now, for this video, I put together this diagram. When it comes to powering things, there's a lot of confusing things to look at. And so I hope to cover some of them here. What I'm going to focus on is a particular situation where we're going to light an LED. And so there's all kinds of voltages we can use. If we use a lithium-ion 18650 battery, we're probably going to have an average about 3.6 volts. You can charge them to 4.2 volts, and you should really stop powering stuff with them once they reach about 3 volts. And so, with the lithium-ion batteries, I just took off the little seal there before I started filming, and they're not brand new. I bought them a while ago, but I have not used these 18650 batteries yet. So these are EBL, and I really like these. They cost about a couple dollars, and when you buy them in bulk. And so it says 3.7 volts. That's a way it can kind of look like you get more power out of them than you actually do. The average is actually probably closer to 3.6, but they'll do that. But in any case, it says 3,000 milliamp hours. And the math that I did is for 1,000 milliamp hours because it makes the math easier. And we're going to average about 10 milliamps of current through the LED. So, powering with this particular circuit, an LED with this battery, if I charged it up, we'd probably get, well, they claim 3,000 milliamp hours, but I actually tested these before, and I got about 2,000 milliamp hours. But in case, we could get 200, 300, if this were accurate, hours to light an LED. So, I'm not going to actually do that test. We did the math. But the main thing is, we can also, if we need a higher voltage, just put the batteries in series, like that. Connect them end to end. There's holders to do that and whatnot. But in any case, first we'll look at the voltage of one of them. So these have a little button on there that you can make a connection to pretty easily. And there you can see about 3.65. That's what they are when I first take them out of the package. I haven't charged these or use them to power anything. And we're just going to simulate using these. There you can see about 3.6. We put them, so they're about halfway charged. We put them in series, we connect them end to end, and I got the black probe down here. There you go, you can see it all. And there you can see a little less than 7.4, which is what we expect when we got two batteries, or 7.2, when we got two batteries at 3.6 in series. Their voltages add up. And so that's really nice. If you need more voltage, you can keep adding batteries in series until you have enough voltage. That's pretty straightforward, pretty well known, and there you can see I did the math. For two 3.6 volt batteries in series, you get 7.2 volts. Now, when it comes to this video though, so I'm done with the batteries now. We are just going to use a power supply where I can change the voltage manually, because it's going to take forever. We saw hundreds of hours, 100 hours basically, for the voltage to change significantly with an LED. So I can just manually adjust the voltage and just simulate over time. Now, we're going to look at the difference between using one battery to light an LED and then two of them in series with a higher voltage. We will get the same results. The main takeaway though is, with one battery, we'll get 100 hours to hold about 10 milliamps, 0.01 amps right there. So we're going to average it, because with a fixed resistor and LED, higher voltage is going to be more current, lower voltage is going to be less current. So we're going to take that middle point number, and the LED is going to block about 1.9 volts. If that will leave us 1.7 volts from a 3.6 volt supply, and then so 170 ohm resistor will give us 10 milliamps. right there. So that will be the average. Sometimes it'll be higher, sometimes it will be lower, but we're still in the safe range. We're nowhere near exceeding 20 milliamps, and we're not dropping to almost 0 milliamps where there's no light. We'll see it still lights up pretty well. Now, our other option, maybe we have other circuitry that needs, you know, an average of 7.2 volts. So we have to use that power supply. In those cases, it's perfectly fine to use a resistor and LED like you see here with that voltage. But if all you're doing is lighting the LED, using two batteries in series for a higher voltage is just a waste of energy. Basically, we're going to get the same results, but we'll have two batteries that are discharged that we will have to recharge. So I did the math here, and so that is how hot this resistor is going to get. That's what the wattage is. That is the power there. So the wattage for the LED is pretty simple. We got 1.9 volts, and then you multiply that times 10 milliamps, which is the same as 0.01 amps, and you get 19 milliwatts, 0.019 milliwatts. So that would be the same. That's because the LED is blocking a certain voltage based on how much current's going through it. Whereas the resistor takes the voltage across it, and based on its resistance sets the current. So to lower the current from a higher voltage, you need higher resistance, and thus for a given current it's going to get hotter. So that is the main takeaway. Let's look at this scenario first with the single LED. And so I have a higher voltage on the power supply. So the power supply, the output here goes to these probes. It's off right now, and they're not probes, they're jumpers, and there's alligator clips on the other side, and I got them clipped to breadboard jumpers that are powering the rail right there. And so this is a 510 ohm resistor. Before I replace it, I'm going to lower the voltage to 4.2 volts so we don't accidentally power too much through the resistor and LED. I do have current limited to 30 milliamps. To make it safer, we can go over here and put it to 20 milliamps of current, because that means this will lower voltage as needed to make sure we don't exceed 20 milliamps of current in case I accidentally miswire something. So, in any case, now we have our starting voltage of a charged battery. I'm going to take out the 510 ohm resistor, so we're using close to the value that I have calculated. This is actually a 180 ohm resistor, because this kit that I have doesn't have a 170 ohm resistor. So 180 right there. But close enough. And you don't have to be exact in most electronics. You can vary things quite a bit. But we're going to get really similar results. So in any case, now I will hit the power button. We will see that the LED comes on. Right there, once the power button is on all the way. And so we have the LED there. Now, the battery's voltage is going to go down over time. So let's simulate that. We'll go over here, and so now we got 4.1 volts, and then we'll make our way down to 3. So you don't want to charge a lithium-ion battery, most of them. They have their own voltages, but you don't want to charge most of them above 4.2 volts, and you really kind of want to stop using them at 3 volts. You can go down to 2.5. That's not end of the world. But at lower voltages, the chemistry, some bad stuff happens with the chemistry. You can read up on it. But in any case, some people over discharge them all the time, and they think it's okay, but it's recommended not to. So in any case, you can see the LED still pretty bright right here, and we can bounce right between 3 volts and 4 volts. So it is getting dimmer by a fair amount, but there you can see it's still usable. Also, you can see the current that's on here. So this is probably about 2 milliamps lower. It's probably closer to 0.007 amps based on my earlier measurements. This one looks to be a little low, a little off. But there you can see we're close to 10 milliamps at 4.2 volts, and now it's slightly higher, 4.2 volts. It was about 10 at 4 volts. So probably about 12. Now it's probably about 13, more accurately. So we can measure that with the meter to check that. But in any case, this is good enough. You can see we're hovering close to that 10 milliamp range. So now, let us pluck this 180 ohm resistor. And here I have a 510 ohm resistor. So with this voltage, we're still okay. And there you can see that even with that value resistor, it's still brighter. So if you want less current, if you know, 1 or 2 milliamps is fine, you could use that value resistor. But we are going to use higher voltages. So with the 2 batteries in series, which I already showed you that we got the 7.2 with them, both at about 3.6 volts. But we do have a maximum when they're fully charged of, now that they're in series, their voltages add up 8.4 volts. And we'll stop discharging them at 6 volts. But we still just want to light one LED. So it's going to use up the same amount of power. We're going to still put about 10 milliamps of current, which is the same as 0.01 amp current through them. So we're going to need a higher value resistor to limit the current, because we're dealing with more voltage. And more voltage, more than twice the voltage, is going to fall on the resistor, because the LED is not blocking twice the voltage. It's going to block about the same voltage, which for these red LEDs is about 1.9 volts right there. There are, like the green LEDs, they take almost 3 volts, and the blue LEDs that I have, almost 3 volts just to light up. So a single battery, once it gets towards discharge, will barely put any current through them. So that'll be probably added to a later video. But in any case, for the red LEDs, so you may actually need 2 series batteries for certain LEDs. But this one, we just saw one did okay. Now, it's still only blocking about 1.9 volts. So now there's about 5.3 volts average across the resistor right there. And so the wattage is quite a bit higher from the calculations right there. So we'll have an average wattage of 0.017 watts, which is nowhere near the 0.25 maximum wattage or the 0.125 recommended wattage. So we're still way below that. Even with this setup, it's higher, but it's still nowhere near the 0.125 watts. So we're really good to go. So I already swapped out the resistor. Let's go over here. And as you can see, 4 volts, it's still pretty bright. But we will move this up to 8. And then we will go over here to 8.4. So there you can see that's pretty bright. And I'm just going to drop down volts at a time until we get to 6. So it got dimmer, but it's still pretty bright. And if we're using lithium-ion batteries, that's a good point to stop discharging it. It's a good time to recharge it, because we got 3 volts across each of them. Hopefully. That's another thing. Batteries don't discharge evenly. One might discharge more than the other. So that's another reason why, even though technically you can go to 2.5 volts, it's better to hold it 3, especially in series. 3 per cell, because one of them might have discharged more than the others. So that's topics for other videos. But in any case, main takeaway is, as I said before, with this setup, if it's a 1000 milliamp hour battery, and you take 10 milliamps that it is flowing, so as you can see, that same 10 milliamps is going through both of the batteries. They're both putting that 10 milliamp hours through there, so they're both discharging at the same rate, which will give you about 100 hours of usable power. Same with the single battery, lighting the exact same LED to about the exact same brightness, close enough, and again, 100 hours, but now you just have one battery that is discharged. So you only have to recharge one battery. So it's using basically half of the stored energy for batteries. So we could take, instead of 2 in series, we could make this circuit, put them parallel. Each one of them will provide 5 milliamps of the 10 milliamps. So they'll last twice as long, because there's twice the batteries when they are parallel. But when they're in series, the current flows through both of them. So they're both putting through 10 milliamps of current. And so they're both going to still live by this time. If they're 1000 milliamp hour batteries and they're providing 10 milliamps, they have to push harder because there's more resistance here to keep that 10 milliamps versus the other one. And so they're just using up energy without getting more results from the load. So in any case, hopefully that all made sense. This is a quick bonus video I put together. It took me, I think, no more than 2 hours to get all of this set up. So hopefully in the future I can explain this stuff better and provide a lot more examples. But I thought this would be a great video idea for right now. And it's 16 minutes now that we're running up to. So it took a lot of time. I'm glad I didn't make it a more complex video. So thanks for watching. I will see you in the next video.